How's it going, ladies, gentlemen, and non-binary? I'm Amelia Thompson here, and joining me back in the studio, but from across the pond, is Thomas Robach, ICANN Technical Principal, Academy Principal with our Connectors Division at Würth Elektronik in Germany. Today, our topic is RF behavior of pin and socket headers. We're very excited to have Thomas joining us again for one of our final webinars of 2021. If you have any questions throughout today's presentation, make sure you are asking them in the questions box. As always, feel free to send us a greeting, send us a welcome, let me know how you're feeling, let me know what projects you're working on. A lot of people like to talk about different inventions that they are creating. If you have an application really relating to today's topic, you can ask the questions and Thomas will answer them at the end. Now, if your question doesn't get answered, maybe you think of it a little bit later, maybe you need some really in-depth technical assistance, feel free to reply to our follow-up email. You'll be receiving that within the next couple of days, and it's here for you at we-online.com. Simply reply to the follow-up email, which brings us to our next topic. Because you registered for today's Würth Elektronik webinar, you will automatically receive the video on demand and the presented slides within the next 24 to 48 hours. Because it's a Saturday, you might get them Monday, possibly even Tuesday. We're going to try to get those to you as soon as possible. We do have a few welcomes rolling in. Chip, I see you. Hello, good morning. Are you Chip from Australia? I'm really curious about that, but welcome from way across the pond. Again, if you have any questions or a warm welcome, feel free to message us in the questions box. Like I said, only a few webinars remain for 2021. Our final English webinar is actually next week, Advanced EMC Shielding Grounding Edition, coming up on Wednesday the 13th. And then Fabio Costa wraps up our 2021 webinars with his presentation in Portuguese, and it is on our passive components, specifically EMI, and that will be October 20th. There is some potential for a surprise power webinar with an IC manufacturer. Be on the lookout for that, and you can register for all of our webinars online at www.we-online.com/webinars. Of course, all of our webinars are made possible thanks to our exclusive sponsor, Digikey Electronics. We are really happy that they have sponsored our webinars for the third year in a row, possibly looking for a fourth year in 2022, and we have some really big news. Be on the lookout for that. Now, I'm going to hand it over to Thomas Robach as he proudly presents RF behavior of pin and socket headers.
Thank you for the warm welcome. It's always a pleasure being here. So first, I would like to try to share my screen with you to make my content visible and to organize myself. And I hope this is working nice. Yeah, my name is Thomas Robach and I'm working for the division of ICANN at Würth Elektroniks. And today's topic I want to introduce to you is the RF behavior of pin headers based on an example of a WE pin header 1.27 millimeter. And of course, we are not only talking about the pin header when it's about RF, but about the combination between pin header and socket header. Otherwise, it's a little bit useless since you don't want to use it as little antenna array. What I want to do today with you is a couple of things. So first, a little bit of introduction, where it comes from, how we selected, what to measure, how to measure, to explain the measurement setup and target, which is important, of course, to have the right understanding for the values afterwards. In between, we will have a look at some important parameter to explain where it comes from and why we measured them. And at the end, of course, I want to show you a little bit what to do with the measurement results, what you could do with them, how you could use them, just to give you some idea before we have the final summary. So where does this all come from? Basically, it really comes from you, or let's say in this case from your colleagues, because as I'm from Europe, most of the questions have been coming from there. So I still have contact to customers. I still have contact, of course, to our application engineers that are with the customer, and we got a lot of questions from the customers. Hey, can you give us some more details on what these kind of connectors, these tiny little pin headers, can do in point of signal transmission, in point of RF? And as it's very much standard connectors, usually you don't get data for that, you don't have it. So we thought about what can we do for the customer to support them and to give them more insight on what these connectors are capable of. And so the first thing what we did locally is we made a little PCB for them where they could test whether a USB signal can be transferred. So you can plug a USB stick, plug your computer on the other side. You have a board-to-board connection with this 1.27 pin header, and you can check if this is working or not in your combination. And on the other side, you have these coaxial connectors on the board, also with a board-to-board connection with the pin header. So if you have your individual single-ended signal, you could try it out if it works. This was quite nice to have it locally with the customer to test it. So when the ADM goes out or the FAE goes out, but still we could not provide some real data. So we have been thinking about how to do that. And out of the experience and also discussion with the customers, well, we defined the area, what we want, where we want to be, what we want to measure. And we started, of course, to make some test boards, some calibration board for the test board to measure these connectors. So frequency range, the frequency chart, the classic areas are from very low frequency to extreme high frequency, I think everybody's familiar with. And for those connectors, we decided to go for the area of 300 from 3 megahertz up to 3 gigahertz. That's what we wanted to measure. Because out of the experience, we knew that in the lower frequencies, it's not a big issue, but it also does not really make sense to go much higher. So we are targeting more in the center of the area, of course, and a little bit above. So what is typical signals that appear in this frequency area that everybody knows? So this is just examples to give an insight or an idea about what frequencies we have here. So if we look typical computer signals, but that everybody knows, just to give a glance. So FireWire 400 with 400 megahertz should be working. 800, well, could be a big question. USB 1.1 should be working. USB 2.0, who knows? 3 and 3.1 USB, of course, it's much too high in frequency, will not work out. PCI Express, maybe. We need to see what the results bring. And PCI Express 2 and 3 are too high, definitely, from the frequency, because with the signals, typically you have that your fundamental frequency is half of the tact frequency, and you want to transfer at least the second harmonic. So if you want to transfer, for example, USB 2.0 with 480 megahertz, then base frequency is 240, and you're close to 1 gigahertz to transfer if you want to make it work properly. So that's the idea behind of the thought. And well, why do we have to take care on that so much? Because when we talk about RF, then it's a little bit different than with the low frequencies. For low frequency, the physical effects are quite or a little bit easier to describe. And so we could, in RF, we have interaction of magnetical and electrical fields, and this leads to complex relations and a lot of influences of connector geometry, all that kind of thing, where we have to take care on, because when we go for the high frequency, it's really also a matter of material and structure of the surface, how good we can transmit signals, what materials, what basic materials we're using, what contact geometry we are using. So this also matters, and of course also the type of mounting, whether we are talking about SMT, THT, pin geometry inside of the connector. So are they bent in sharp corners? Are they more smooth? All that kind of things have impact. And of course, a real RF connector that is suitable for RF applications is usually designed specifically to the requirements of a certain, and brings its performance in a certain frequency area. And as we have standard parts here, this is of course not really specified from scratch on the datasheet. And so the interest is of course to find out, where can we go with this? What can we really do with a connector like that? Therefore, we need to talk about a few parameters, and we need also to look how we can use these parameters and display them. Of course, the first we need to talk about is the insertion loss. So it's the loss of the signal throughout the transmission line, and we want to have as low losses as possible, of course. It's usually expressed in decibels, and it's a sum of losses. So insertion loss includes all losses on the transmission line, as well as heat losses by the Joule effect, but also losses caused by reflection and radiation. So this is all included in this insertion loss. And if we look a little bit deeper on the dB values, then we can see that if we have an insertion loss of 1 dB, we already have a loss of 20% of the signal. If we are at 6 dB insertion loss, we have already lost 75% of the signal. So it's really important for us to keep it low. The second important parameter is the matching. So the picture here is just, let's say, a parallel more or less from optics. So it's the frequency dependent loss because of signal reflection. So it's a detail more or less of the insertion loss. This gives us information about how good our system is matching to the correct impedance. And if we take the example regarding optics, if you have a very good surface, plane surface, then you have nearly no loss and your light will be reflected in one nice and good angle without a lot of distortion or misreflection. But if you have a mismatching and you have an uneven surface, you get reflections not only in one direction but in different directions. So you have a lot of loss of energy, and if we have mismatching on our transmission line and therefore reflections, we also have a loss of energy in that case. And also here, if we look on the decibel values, so we can say that we have when we have 6 dB, we have 75% of signal and 25% of reflection. If we have 15 dB, we have 97% of signal and 3% of reflection. These values you will need later on, of course, when we look at the measurement results. And the third one, what we have been measuring, of course, is the crosstalk, because this is becoming important when we have more signals running through our pin header on the pins. So it's the phenomenon where a signal that is transmitted on one circuit of the transmission system creates an undesired effect in another circuit that's running parallel to it. So it's usually capacitive or inductive coupling where you have these crosstalk effect. So you typically have an aggressor trace, and it influences the parallel running victim trace and will so distort maybe your signal running on the parallel trace. Here we of course want to have the impact as low as possible. So best case, we have no crosstalk at all. But the better the separation between the aggressor on the victim trace is, the higher the dB value is in between, the better it is for us. So in this, and for the measurement of the crosstalk, we also thought about different layout configurations, how we could maybe optimize this. We will see then in the layout description later on. So how can we now look at these parameters that we measure? What can we do with it? How does this signal come? So if we start from scratch and go back to our example for USB, for example, or any digital signal, more or less, if we transmit a signal on this transmission line, we typically have for the digital signals square shaped signals. And how do they come? Well, if you have the base wave, fundamental wave, and you add harmonics. So here you see the first, first wave, the basic wave, and you have the first and the third. So basic wave and the harmonic added. So you already see if they add each other, they become more related to a square. And the more harmonics you add, the more closer you come to the square shape of the signal. You can bring this to an extreme, of course, which you can see here. So we already saw the fundamental wave and a few of the harmonics, and the gray one, which is nearly rectangular, is then up to the 29th harmonic. But the question is always, how many harmonics do you need? Because the more harmonics you transfer, the higher the frequency is that you need to be able to use. And of course, this kind of connector is not thought to be used for any measurement application or whatever. So it's just, does it work or does it not work? Does it safely work in my application? So it's about making the signal work. So we should be able to transfer the third harmonic to make it normally work. If we measure with our network analyzer, that's what we did for our examples, then of course we also have the display of the network analyzer that shows us what we measure. And so this is what I added here, just some examples. So we have the S21, which is the measurement of the insertion loss of the transmission line. We have the S11 and 22, which is the matching, which we can see here below. And on the other side, we have the measurement of the crosstalk. So that's the impact on a victim trace. So that's what's left from the original signal and has been coupled to the victim trace. Another way of displaying the measurement results is also the possibility to show it in a Smith diagram. So this is a method to visualize the impedance depending on the frequency, and it's based on a unit circle where a complex system of coordinates is projected. So based on the calculation of the imaginary numbers, it shows the real part, and the imaginary part of the different on the different axes, and therefore we can see here, or we can read out here, positive and negative reactances. So the positive ones are inductive effects and the negative one are capacitive effects. So this is, of course, just examples from the calibration of the system, but this is also something we can create out of the measured parameter, because there's a couple of different free online tools where you can integrate these existing or measured S parameter sets, and then you can get the according Smith diagram about it to judge how it behaves where, so to make your conclusions. How did we measure it? So what was the setup and what are we targeting on? This is the question for, or the topic for the next chapter, and we tested different PCB layouts, and now I will explain you how we did it. So the measurement was done with a 2-port analyzer that can do up to 5 gigahertz. We did not use it up to 5 gigahertz completely, as it does not make sense for these products. And of course, we used termination resistors and measured in a 50 ohm system as usual. And of course, we had our testes and we had some calibration board made so that we could shift the reference point from the end of the measurement cable to the pin of the connector, because of course we don't want to measure the coaxial connector and the part of the transmission line of the PCB, but we wanted to make it as precise as possible, just to measure really from, let's say, the soldering point on the bottom PCB to the soldering point of the top PCB. This is something we cannot avoid to have some impact of that, but we try to be as precise as possible. So how did the layouts look like what we measured? The first one we did is, of course, the basic idea. So we bring a signal into the first SMA connector to one of the pins of the pin socket handler combination. Then it goes up to its counterpart on the top PCB and goes out to the according coaxial connector. And we do exactly the same on the opposite pin here. So that's the important point. So this is the closest distance between the two pins. This will have not a lot of impact on the insertion loss or on the matching, but it will have definitely impact on the crosstalk. And this is also the reason why we suggested 2 different layouts, because it is just about the insertion loss and matching. Then okay, we could just measure the different pin combinations, that's it. But for the crosstalk, we need to measure 2 lines at the same time. That's why, so that's the keying of the components, so that we can see quickly when we have it in hands, oh yeah, that's the 2 pins we are using for the signal. And here just a photo of how the testy looks like. So you can see we have soldered some distance holders to be able to make a good board-to-board connection that is stable and so on, that there is nothing moving. And this is just a snapshot of the layout where you can see the trace coming in from both sides and going out on both sides. And the second layout is a little bit different. The basic idea is the same. Everything that is not needed, of course, goes to ground. And you can see it most easy here on the keying. What we did on the second layout is we swapped the relation of the pins so that we are not opposite, but we have a little bit longer distance. It's diagonal here. And of course, we have these ground pins here, so that we hopefully have also some positive effect from that here. In the third, oh, I forgot, here, of course, same pictures of the testy, the keying, and of course, the layout snapshot where you can see that it's shifted. For the third layout, we brought it to the next level because we thought if people are using a very tiny pin header like a 1.27 or could use that, then maybe if they need to transfer a faster signal safe, they maybe are willing to let's say give the space for an additional pin row to make it safe. And that's why we come in here on one pin, and then we separate the two signal pins with a line of ground pins and go out here on the other side. So you can see it easily here on the keying, the two pins that have the signal, and there is one line of ground pins in between. So again, here the keying picture, and here you really see the distance between the traces. So what is the target of all this? Why are we doing this? Because we get a lot of questions about it, and this brought us to the point that we wanted to gain additional knowledge about the performance and also application possibilities about our pin and socket headers. And the questions were, in this case, mainly on the small pitch. So this seems to be very popular for that and space saving. So that's why people like it. And we wanted to gain some significant measurement data as a base for evaluation, so also to be able to support our engineering customers. And with that, we could offer more detailed know-how about standard products where it's not typical to have that. And what I will show you now, we wanted to offer also, or to show an additional tool to our customer that possibly can make the work easier. And that's the next thing I would love to show you, because we have been searching for a possibility how to show you all the measurement data we did and to compare them across the 3 different layouts. And of course, you could make screenshots, overlay them, and so on. But this is not really interactive with comparing it with other things. It's just a picture. So we found a possibility to import the measurement data into the Ltspice program. And the benefit of this is that we can directly compare our curves to get also in this training, but you can also use this to see what influence the part has on a circuit if you use these data for simulating with Ltspice, because even if it's not 100% accurate, it's still a lot better than making 10 test boards in different configurations, check out, make a new one, and so on, which is very time and cost intense. So a simulation in advance can, of course, help, let's say, to avoid the one or other test board that you otherwise need to do. And this is the first I want to show you how to integrate this data into Ltspice. So we want to integrate the measurement data. We want to see how we can use it. So how we can bring, let's say, our measurement system, the measurement device with the data into Ltspice. And then we can compare the data of the different layouts to see what impact it has. There is a nice little tool available on the web. If you go for it, if you search for it, that someone programmed, it's called Ltspice. So it's not from us, but it's really great for help for that. This is why I'm highlighting this. And it's able to, what do you call that in English? To transfer the S-parameter files in touchstone format that is coming out from the network analyzer to Ltspice library files that can be used in the Ltspice. This is very, very helpful. And the cool thing with it is this is not only working, of course, for a connector most of the time, I think it's used for other parts, because for many RF components, you don't get an Ltspice model, it's not available, but you get for most of them S parameter sets that are already measured. And so you can convert those to library files for the Ltspice that you can, and you can find this converter on Internet Tech Group. So you just have to Google for the S2 Spice converter, and then this will be easy to do. And this is what I will show you next if I am able to arrange my screens accordingly. So sorry if I blend in something wrong in the beginning or something like that. It's a lot of programs open, and we will see if I'm able to do it live, because it's no problem to do it for myself. But when you're talking in front of people, it might maybe be a little bit more difficult. So I prepared already a folder in my Ltspice program folder, and I put here two things. The one thing is the S2 Spice file that you can see here. So that's the converter. And the other thing is I just put here a S parameter set coming from the analyzer. That's just one of those we created, so doesn't matter which one. This is just showing now how the converter works. And to work with that one, you need to open your command window on your computer. So if you don't know how to open, if you enter into the search field on the bottom left of your window, CMD for command, then this window will open. So we are now, as I say, at my age in DOS mode. It's not really anymore, but I still know the old DOS versions. So that's very helpful in this case. So the first thing I do is I go back to the initial directory and I make it step for step. You could also combine it to go directly to the right one. So now I'm back in the initial directory, and then I use again the CD directive, which is change directory. And now I need to use this path here. I take it with copy and paste, which is now working, which is great. In the last Windows version, you could copy it, but you had to paste it with your right mouse key. Now this is all working pretty well. And now you just have to execute the file. So you say S2 Spice, what's the name? /097. Don't forget to enter the extension, otherwise it will not work. It's an exe file. And now you need to add the name of the file you want to convert. I also take it by copying and oh no, I need to copy the full one, including the extension. And if I enter it here, so I tell him you have to convert that file. And when you now click enter, it will ask you for how many measurement ports you had. In our case, we had a 2-port analyzer. And so I say 2, press enter, and it also already has processed it. And you can see now here that we created a library file. And this is now an Ltspice library file. This is pretty great. Of course, I would usually put it now in the Ltspice library folder where I have all my others already. I just separated it for my organization in that case. So we can leave that one. So we converted the files as we wanted to. The next one, what we do is we go to the Ltspice, if I can find it, because now we need to get our measurement library files into the Ltspice. How can we do that? Of course, we go for a new schematic first, and then there is a nice little tool also that also needs to be downloaded and brought to the components folder of the Ltspice before, because this is called S2 port, and it's not included in the Ltspice as far as I know, basically. So you have to download it from the internet and integrate it. If you have that one, that's our, let's say, core of our simulation system. It's the black box that we link to the measurement result data. And we need, of course, also some other things to make it work. We need to have, of course, a voltage. So some source. And we should also have in our system a termination resistance, which is also very useful. And then we need to combine the whole thing to link it. And I forgot, we need some ground connections. Otherwise, without ground connection, we will not have any signal result. Then we set, of course, the termination resistance to 50 ohm. And we also give the source, of course, the 50 ohm. We are in a 50 ohm system. That's pretty nice. So we are prepared now. And now we need to tell this box what is the file you need to use, where you need to use the data of. For this, we need an Ltspice operation, and the directive in this case is .lib for library. And then you add the path where your file is saved. What is a little bit uncomfortable here is that you don't have a browse button in the first stage. So you would have go to your Explorer, copy the path and so on. Or another thing, what I found out, which is pretty nice, if you just add .lib here, click on OK, and then you go on it with your right mouse button and it opens again, you suddenly have a browse button. This is a little bit of a surprise. I don't know why this happens like this, but I find it very comfortable to work with the browse button. So this is why I want to do that. And now you can choose which library file you want to use. I take the first one here, open it. Okay, and now you have the full file path that you want to use here on top. Now we have the library file integrated to the Ltspice. Now we just have to tell this box that this is the file it should use. And we could do that easily. We need to use the name of the file here. I do it again with copy and paste. So I mark it here, if I can grab it. And important in this case, you don't need to have the extension. If you copy the extension, you get a failure window. So we click also on that box with the right button, and in the value name, you now simply paste the name of the file. That's it. What did we forget? Oh yeah, we should also turn on the voltage source. So just set the AC amplitude to 1 here. And I think we are done so far. Let's have a look if we are done. Let's make it run. Ah, yeah, okay, of course, we have to tell him the data, what sweep type we have, in our case, octave, the number of points per octave. I set it to 100. The higher you set it, the longer it will take to calculate it, the more dense the data is, and the frequency range. So let's start at 300 megahertz and end up at 2 gigahertz, and then it should be fine. Yep, no failure window, so I forgot nothing. That's pretty great. Now you have the black field here, and with the right mouse button into that field, you can add traces. And now you see what you can choose of, but we forgot one thing. So now you have just the different, well, current and voltage curves you can choose, but you cannot choose the S11, S21, and so on. So your measurement port combinations. This is due to the fact that we have to enter one more Ltspice directive. So let's cancel this here. And this is the .NET for the network device, and we have here the voltage one, the resistance one. So we have to have the current over the R1 with the voltage 1. I think that's it. Okay, put it somewhere here. And if you let it run again, are you done? Yes. Add trace, then you can see here now, now I can choose, very nice, my combinations of ports in the S parameter. So I could choose now the S21, which is my insertion loss, and then I will see it over the frequency range for that one. Of course, we don't want to go to all that single for each curve, but we want to see the combinations and the impact on the different layouts. So I prepared already something. I will close all that. This was just to show you how you can integrate the data into the Ltspice. And now we can open the prepared files. That's 2 files in this case, because due to the fact that we only had a 2-port analyzer for that, we needed to change the how it was connected to the testee, because for the measurement of the crosstalk from the suppression, we needed to use, of course, 2 termination resistances at the end of the transmission line to be able to measure 2 tracks at the same time. One where we put the signal on and one where we measure what is the impact of the signal. That's why we have 2 different setups here. Let's start with the first one for the insertion loss and the matching. What you can see here is the same what I just did, but with the values on the left for the first layout, where the pins are really directly opposite of each other. The second layout, where the pins have been shifted a little bit diagonal, and the third one, which was with the complete pin row of ground connection in between the signal path. And this is what we will have to see now. If you let it start. Yeah, and I will make it a little bit bigger, and maybe we could also, yeah, grid is in. So let's first add the traces for the insertion loss. So this should be my S21 traces for the 3 layouts. And in best case, I add all 3 at once, because in best case, they should be quite identical, because if I measure the insertion loss of one transmission line in 3 different layouts, we said we shift the reference point to the pins top and bottom, so that we really only measure the connector. So they should be very similar. Of course, there will be some deviation depending on the soldering, depending on manufacturing tolerances, all that kind of stuff, but they should be very, very similar. And we can see that's the case. They are quite similar, up to 2 gigahertz. And you can also see when we are at 1 gigahertz, what loss do we have here? We are talking here about roughly minus 32 dB, something like that. And if we go, oh, sorry, that was at 100 megahertz. So we are roughly here at 1 gigahertz. So we are at minus 160 milli-dB. So overall, the biggest loss we have up here is minus 320 milli-dB at 2 gigahertz. So that's basically what's coming out, and we can see they are aligned quite nice. And of course, the higher the frequency get, the higher the impact of the tolerances is. So the more deviation we will have. But basically, the picture is quite nice. So let's have a look at, oops. Let's have a look at the matching. Just delete these traces here, not to have too much confusion on the screen. And we will add the traces for the matching, which is our S11 or S22 traces for the 3 different layouts. And we can see here with the matching, we said we want to have it as low a low value as possible. So we are starting about minus 80, minus 86 decibel, and with rising frequency, of course, the value also gets lower here until we reach finally at the highest point. We are something like minus 20, 22 dB here, and also here we see, as it should be, the lines or the three layouts are quite aligned to each other, so the deviation is not too big. That's quite okay so far. The interesting point now is, so here we know, okay, our tolerances are better than I expected, honestly. I had a lot of headache about that when we started the whole thing, if the different testes we did, because it was not only 3, it was something like 20, a little bit, 22, 23 as far as I remember. And I was really afraid of having big deviations here due to manufacturing, but it was really not the case. So I was very happy about a quite stable result. And now finally, we could have a look on the crosstalk of the pins, because this is becoming very interesting when you do not only want to transfer single-ended signals, but if you go to signal pairs, stuff like that, then of course you should be aware of the crosstalk that is happening in between the different pins. And oh yeah, I have to open the new file. So for the crosstalk, we have that file. The setup basically is the same. It's just another S parameter file that is behind because of different connection from the measurement equipment to the testee with the termination resistances. So if we let it run also here, takes a while. Then we can look at the different traces step by step. So if we take the first one, so we indicate it, or we send signal to the first pin and then measured on the second pin what or how much influence we have in relation to the original signal, and exactly this part that we could measure on the second pin is what we will see here. So in the first one, where the pins are directly opposite to each other, so most close to each other, as close as possible, I would say, we can see that we start at around minus 88 dB and grow up, of course, with growing frequency, with rising frequency, up to at 1 gigahertz here, something like minus 26, 27 dB. So this is not such a beautiful result as we wanted to have it. So in this combination, probably you should stay until somewhere here, something like -60 dB is a quite good value, or below. So this really reduces the usability, let's say like this. And this is also the reason why we thought about the 2 additional layouts. And now, come on, put it away. Make it more clean, then it's easier to see. Now we will add the second trace, which is the diagonal pins. So just shifted 1 pin row to see how big the impact is on the result and how much more you can gain with that. And this would be now my version 2 as to one of my version 2. And if I add it, I can see already only by increasing the distance a little bit, I gain more headroom for that. So if I want to go below my -60 dB, I'm roughly a little bit below 100 megahertz. It's already better, much better than if I have them directly in parallel, but it's not perfect yet. I would love to have a little bit more still, because finally I want to safely transfer signals like USB and really make it work, and not to have to tremble and think about if it's working the whole time. So, and that is where layout number 3 enters the ring, and that's where we separated the 2 the signal pin and the or the 2 signal pins with 1 row of ground pins. So we did not only increase the distance now, but we added also the ground separation with the 2 ground pins in between, in the hope that this will get an even better result than only increasing distance. And we will see how this looks like. This was my S2.1 from the version 3, so from the layout 3. And we could see that we really have a bigger influence here. Because if we now search for our -60 dB, we are here. So we are already across 1 gigahertz. So this is really working pretty well. And if you want to transfer signal pairs or signals that should not influence each other, this is really helpful and a very well spent space to do something like that. Especially as these kind of connectors are really tiny, so you don't really lose a lot of space if you bring 1 row of pins for grounding into the layout, and it secures you when you want to transfer data on it. Yeah, so the final result is honestly, the results have been better than I expected for that tiny standard pin header that is not a lot of cost and so on. So it can do really more than we expected. It's capable of transferring more signals or data than we thought. And I also summed this up at the end for you, because you will have the presentation afterwards. So for all these 3 layouts, I gave you the values here for insertion loss and matching, always at the 0.1 gigahertz and 2 gigahertz. I also put in this case, pictures of the screenshots of the Ltspice. Okay, this is an older version of Ltspice, but the data behind is the same. That shows you the 3 tracks in for the insertion loss, for the matching, and for the crosstalk, so that you have at least some idea about what they're capable of, where you can use them in addition to just have some small current circuit or analog signal on it. And if someone is interested for these 1.27 millimeter pin headers, I also have the measurement data for the Ltspice integration. So if someone wants to play with it, I can also provide this because I did this all by myself. So we have the data. It's no big deal to support you if you're curious how this will work in your layout idea or your Ltspice simulation. Yeah, that's it from my side for today, and I hope it was interesting to you. And if you have any questions, of course, you're welcome as well now or also later on by email. Thank you very much.
Thank you, Thomas, for presenting today's Wurth Electronic webinar. Again, if you have any questions, feel free to ask them in the questions box. And if you do think of questions later on, maybe you want to go into more technical detail, then we will gladly answer them at the end. One of the questions that did come in was, where can they purchase the design guide for Ltspice?
Oh, the design guide, you mean the book?
Yes.
Yeah, the book for Ltspice, of course, can be purchased via us, you know, the big blue one. With Electronics offers a book, and honestly, I learned a lot of that about that. So it appeared the first time when I started with the measurement, really, where I really had to use it. And the cool thing with it, the guy that wrote it, he wrote it really based on questions coming up on Ltspice for a couple of years. He really collected that and really tried to answer that. So this is why it was for me really helpful. I was really a new starter with that when I started with that measurements with the Ltspice. So not with the measurements, but with Ltspice, I was a new starter. And it was for me like, hey, cool, I don't need to have that all, but I can really find answers to my question where I don't find my way. So I can really promote this very well because it was really a help to me.
And we've heard some really great feedback about the Ltspice manual. They recently have a new revision to it, and I believe it can also be found as an ebook. I think it was recently put online as an ebook, and we can also include that link in the follow-up email. Don't see any questions coming in right now. We'll wait just a couple more minutes. And again, if you have questions, simply click on the questions box and we'll get to them.
You know what's really cool? I also learned something new. I didn't know it's released as ebook. That's really nice and a good help because the printed version is quite huge, so it's quite heavy.
That it is. I believe it was one of the, I believe, you don't quote me on it completely, but if it is released as an ebook, I'm going to try to include that link. I do know that our trilogy of magnetics was released as an ebook. And I also want to say our trilogy of wireless power transfer. So to help as everything is going to a digital format, which makes downloading to the Kindle a lot easier.
And it makes it so much easier to search for keywords if you're facing an issue and you just want to find quickly the keyword.
Absolutely. We do have a question here. Since this person is not familiar with the S parameter notation, is it possible to calculate differential impedance for the different configurations using the Ltspice method?
So with what we did here with that measurement, it will be hard because if we would have measured it complex to have all tracks in one layout and in one set of data, then you can do something, but not with the data we have here. This is really, we need to do it on a full port to have the complex measures. So this is really for simulating the single lines or for having just seeing the influence from one pin to the other in point of crosstalk, but it's not really possible to do the matching that way. Unfortunately, we did not have a bigger machine at the time, at least not at my access.
Understandable.
This is a project in the near future to have it as everything in one parameter set to really have the complex parameters. This is already ongoing, so I'm already preparing the PCBs for hiring for purchasing.
Okay, we have another question that came in. Do you expect 2.54 headers to be twice as good?
Good question. So I know already a little bit about them because we had also, of course, a look on those. And the point is, in point of crosstalk, of course, they have bigger distances in between the pins. So if you do the same with what we did here, in point of crosstalk, you will get a little bit of better result, definitely, as you increase the distance. But in point of distortion and matching, I'm not pretty sure because the surfaces are a little bit different. They are more, if you talk on a microscopic level, more uneven. So I don't think that the overall result will be so much better besides the crosstalk.
All right, thank you. We do have more questions rolling in now. People have warmed up their keyboard. We only have time for one more question. And again, all of these questions will be answered after our webinar. Our final question for today. Thank you for showing that pin layouts can mitigate coupling on 1.27 millimeter pitch, but what pitch where it becomes required to have filters and other hardware mitigation to limit noise?
That's a very good question. I honestly cannot really answer because that's the smallest pitch we had in the portfolio. So we did not really measure a smaller one. If we go down to 1 millimeter or 0.8, what happens there? But it's a very interesting one I already have in my mind for the future. Because of course things are getting more small, people are trying to build smaller, and this will have definite impact on that. So yes, this is something that is becoming more and more important, and as also we also go smaller with our parts, I think I will have some additional hobby work in the future besides my normal tasks.
I think you are absolutely right. Our applications are smaller, thinner, and more powerful than ever before. I remember carrying around a bag phone in a car, and to now be able to put my cell phone directly in my pocket, it's absolutely ridiculous. Who would have thought?
Yeah, and it's
Well,
developing
that
really fast.
absolutely. That ends today's Wurth Electronic webinar. Thomas, thank you so much for presenting on RF behaviors of pin and socket headers. For everybody that has joined us, thank you for joining one of our final webinars of 2021. And don't forget to listen to the new Wurth Electronics What's Up radio podcast. Each week we are bringing application notes, webinars, blogs, press releases to a completely audio format. This week's episode is hot plugging of PoE modular jacks, and that will go live today, actually, at 12 p.m. Central, just about an hour or so, and it will be live on Spotify, Google Podcasts, iTunes, anywhere you listen to a podcast, it is available. You can also listen to our podcast at we-online.com/podcast. Like I said, only a couple more webinars remaining for 2021. Our final English webinar is Advanced EMC Shielding Grounding Edition. That is next Wednesday, October 13th. And then Fabio Costa returns to wrap up the year with his EMI presentation on October 20th. That will be in Portuguese. There is a possibility of a surprise power webinar with an IC manufacturing partner, and look at we-online.com/webinars for more information on that. Well, I hope to see you back next Wednesday for our final English webinar. Until then, I'm Amelia Thompson. Thank you so much for joining us.